When most of us learned about the pH scale back in high school, we probably learned that it's a scale from 0 to 14, with everything below pH 7 being acidic and above pH 7 being basic. In reality, however, this is a great simplification of the concept of pH. If we measure the pH of water at 37 degrees Celsius, which is body temperature, we see that the pH is 6.8. And the first thought that comes to mind is, aha, this water is acidic because its pH is less than 7. But I can assure you that this water is neutral. After all, if heating up water made it more acidic, then drinking hot tea or coffee would be a very dangerous experience. To understand why this is true, we need to look at the equation for the autoionization of water. We know that water doesn't just exist as H2O liquid. It also self-ionizes to H3O plus and OH minus ions. From the stoichiometric coefficients, we see that when the water is pure, we always have equal concentrations of hydronium and hydroxide. Therefore, pure water is always neutral. To get from pH to H3O plus concentration, we use the familiar formula where the concentration of hydronium is equal to 10 to the negative pH. Thus, at 25 degrees Celsius, when the pH of pure water is 7, the concentration of hydronium is 10 to the negative 7 molar, and because of the 1-to-1 ratio of the stoichiometric coefficients, the concentration of hydroxide must be the same. At 37 degrees Celsius, the pH of pure water is 6.8, so the concentration of hydronium and hydroxide are both 10 to the negative 6.8. So how come the pH and ion concentrations change? That's because of Le Chatelier's principle, which states that temperature changes equilibrium concentrations. And because the concentrations of ions change, so does the pH. Now, what is so special about pH 7 that we call it the neutral pH? In reality, nothing. 25 degrees Celsius is just a common room temperature. And as it happens, the concentration of hydronium and hydroxide in pure water is 10 to the negative 7 at that temperature. And the pH is 7, which is a very nice whole number. So what does make a solution acidic or basic? As you have probably figured out, it is not the pH. In fact, only the relative concentrations of hydronium and hydroxide can tell us if a solution is acidic, basic, or neutral. When the concentration of hydronium is greater than that of hydroxide, the solution is acidic. When it is less, the solution is basic, and when the two are equal, the solution is neutral. Another misconception that you might have is that the formula pH plus pOH equals 14 is always true. While it is true that as you vary the pH at a constant temperature, the sum of the pH and the pOH will remain constant. However, it is not true that the constant is always 14. At 25 degrees Celsius, the concentration of ions in neutral water is 10 to the negative 7 for both hydronium and hydroxide. Thus, the pH and pOH are both 7. So when we add pH and pOH, we get 7 plus 7, which is 14. However, at 37 degrees Celsius, when the concentration of ions in neutral water is 10 to the negative 6.8, the pH and pOH are both 6.8. So when we add these pH and pOH values, we get 13.6. Thus, at 37 degrees Celsius, pH plus pOH is equal to 13.6, not 14. So the takeaway is that there is no single neutral pH. Any pH can be neutral at the right temperature. Because of that, we know that the equation pH plus pOH equals 14 is only true at 25 degrees Celsius. And the pH by itself cannot tell us if a solution is neutral, basic, or acidic. To tell, we must know the relative concentrations of hydronium and hydroxide.
Before, we learned to classify acids and bases as Branson, Lowry, and Lewis. Practically, we usually don't care which of these categories acids and bases fall into. Instead, we care how well an acid or base reacts. So we classify acids and bases as strong, weak, or terrible. Looking at the structure of an acid and base, like hydrochloric acid or ammonia, there's really no way to tell if a species is strong or weak. The way we can tell is by looking at the reaction of the species with water. If all of the acid or base reacts with water, then we say that it is a strong species. If only some of the acid or base reacts with water, then we call it a weak species. And lastly, a terrible acid or base barely reacts with water. In fact, it reacts to such a small extent that we say that it doesn't react at all. Let's first take a look at acids. As we learned in the equilibrium unit, every chemical reaction is an equilibrium reaction. For example, if we react an acid like hydrochloric acid with water, the products are hydronium and chloride ions. The equilibrium constant equals the concentration of the products over the concentrations of the reactants. Remember that we do not include liquids or solids in these calculations, so water is not included. We add an A as a subscript to show that this is an equilibrium constant of an acid.
So let's estimate the Ka of hydrochloric acid at 25 degrees Celsius.
Let's say we start with 1 mole of HCl. We know that hydrochloric acid is a strong acid, so almost 100% of it will react with water to form products. In fact, only about 1 times 10 to the negative 6 moles of hydrochloric acid will remain, so we can estimate that we form 1 mole of hydronium and chloride ions each. If we assume that this is all happening in a 1-liter solution, we can easily convert the moles to concentrations and plug them into the equilibrium constant equation to see that the numerator is much, much bigger than the denominator, by several orders of magnitude. In fact, the numerator is about 1 million times bigger for HCl than the denominator. So, as you can imagine, the Ka is a very, very large number. Specifically for hydrochloric acid, it is 1.3 times 10 to the 6. A large equilibrium constant with a positive exponent is common for all strong acids and bases. Now, let's take a look at a weak acid like acetic acid. Acetic acid reacts with water to form hydronium and acetate ions. The equilibrium constant will equal the products over the reactants. Unlike strong acids, weak acids remain mostly in their unreacted form. In fact, if we had a beaker of 1 liter of water and added 1 mole of acetic acid to it, we would end up with 0.9958 moles of acetic acid, which is almost the amount that we started with, and 0.0042 moles of both acetate and hydronium ions. Let's calculate the equilibrium constant and see how it differs from that of a strong acid. The equilibrium constant is the concentration of the products divided by the concentration of the reactants, which ends up being 1.8 times 10 to the negative 5th, which is the equilibrium constant for acetic acid. In fact, it is typical for weak species to have small equilibrium constants with negative exponents. As we can see, there's a very large difference between equilibrium constants for strong and weak species. So we can easily predict whether a species is strong or weak based on its equilibrium constant. Now, let's take a look at a third class of acids, what we call the terrible acids. These are species that do not react with water and remain mostly in their unreacted form.
An example of this is ethanol. If we were to put 1 mole of ethanol into 1 liter of water, only 1.14 times 10 to the negative 8 moles of it would react.
This amount is so very, very small that in fact ethanol does not even react like an acid. And that's why we call it a terrible acid. We can once again calculate the equilibrium constant, which will be the concentration of the products over the concentration of the reactants, and it will equal 1.3 times 10 to the negative 16. Now, it might not seem that the equilibrium constant for weak and terrible acids are that much different, but in reality, the equilibrium constant for acetic acid is 10 billion times greater than that for ethanol, and that's a big difference. And so, because terrible species barely react, they have very, very, very small equilibrium constants.
Bases follow the same exact trend as acids do. Strong bases react completely in water, and so they have a very large K value with positive exponent. The only difference is that since these are bases, we add a B subscript to the K to make it a KB. Furthermore, weak bases have very small Kb values with negative exponents as we expect, and terrible bases have even smaller Kb values. Interestingly, in any acid-base reaction, the products are also acids and bases. For example, in a reaction of hydrobromic acid and water, the hydrobromic acid is a proton donor, so it's the acid, and water is a proton acceptor, so it's the base. The products of the reaction are a bromide ion and a hydronium ion. If the reaction were to go in reverse, hydronium would donate a proton to bromide to form water and hydrobromic acid, making hydronium the acid and bromide the base for that reaction. And that's why we can classify the products of an acid-base reaction also as acids and bases. We call these products conjugate acids and conjugate bases. If we compare the formulas for water and hydronium, they only differ by 1 proton. And if we look at hydrobromic acid and bromide, we see that they also only differ by 1 proton. We call these pairs conjugate acid-base pairs, because within each pair, one species would act as an acid and one would act as a base.
Hydrobromic acid is a strong acid, so let's determine the strength of its conjugate base. If bromide was a strong or even a weak conjugate base, then it would react with hydronium to form hydrobromic acid and water, reversing what hydrobromic acid just did. However, we know that a strong acid remains almost fully in its conjugate base form. This means that bromide must be much weaker than a weak base. In fact, it is a terrible base. We can generalize this for all strong acids and bases. Their conjugates must always be terrible acids and bases. Ammonia is a weak base and reacts with water to form an ammonium ion and a hydroxide ion. In this reaction, water and hydroxide differ only by one proton, so they are conjugates, and ammonia and ammonium ion also only differ by the presence of one proton, so they are also a conjugate pair. Since ammonia is a base, its conjugate pair ammonium ion will be a conjugate acid, and since water is acting as an acid in this reaction, its conjugate hydroxide will be a conjugate base. Now, let's determine the strength of the conjugate acid of ammonia. Ammonia is a weak base, so it partly reacts with water. Some of it turns to ammonium ion, but a significant amount remains as ammonia. For this to happen, its conjugate acid must also be weak. When ammonium ion is produced, some of it will react with hydroxide ion to reform ammonia, but some of it will remain as an ammonium ion. Had the conjugate acid been strong, then the final solution would only contain ammonia and no ammonium ion, which we know is not true. And had the conjugate acid been a terrible acid, then it would not react with hydroxide at all to reform ammonia, and all of the ammonia would turn to the ammonium ion, which we also know is not what happens for a weak base. Therefore, any weak acid or base will always have a weak conjugate acid or base.